Right, this is a really good example of, a last question or one of the final questions in an exam, which is quite long and quite involved, and brings together loads of different aspects of the syllabus. So the first thing after we've read the question, I'm going to pause and ask you what three main parts of the syllabus you think are covered by this question, just to see if you can get an idea of what's required. Okay, so you've got these two chords, AEC and BED, going across, and you've got various measurements, and they're all these little algebraic terms. It tells you that angle DAE is 48 here, and it asks you to find angle ADE, which is that one, and to give your answer correct to 1 decimal place. So you need to have a little think about what your strategy might be. What do you think this question involves? Okay, so pause the video. I think there are three different parts of the syllabus they're totally different parts of the syllabus, but they're all brought together in this question. Pause the video and have a think about that. Okay, so the first thing is that this is clearly something to do with circle theorems, and one of probably the most challenging circle theorem is something known as the intersecting chords theorem. And I'm going to write this down just so that the examiner knows what I'm thinking. Intersecting chords theorem. And so let's have a quick look. You've got a chord here and a chord here, and they intersect, right? So there's definitely something to do with that. And there is a relationship that always holds when you have intersecting chords. And it is that this part of the chord leading up to the intersection times this part of the chord is equal to this part of the chord leading up to the intersection times this part. Okay? So it's always the bits that are leading up to the intersection of the chord. And I point that out because sometimes you get a funny thing going on here when you've got chords that are outside the circle. So if you imagine chords like, where the intersection is outside the circle, if you've got chords like this, so the intersection is outside the circle here. But you've still got your, let's call it A, B, C, and D points here. So these points on where bound the sort of chords in the circle itself. This is the intersection X, and in this case, it's this whole distance up to the intersection times this distance up to the intersection is equal to this distance up to the intersection times this distance up to the intersection. So it kind of looks a bit different when the intersection is outside, but the thing to remember is it's always the portion of the chord from each of the 2 points that you've got that lead up to the intersection, right? So it's never something like just this bit of the chord, because that doesn't lead from either of the points up to the intersection. Same with this. It's nothing to do with that. All right? So I'll get rid of this picture. Off you go. Okay, so I'm going to write it algebraically here. Intersecting chords theorem. I know that let's change my colour. E times EC is equal to BE times DE or ED, doesn't matter. Okay. So that's what the circle theorem says, and I'm going to use that fact. Now that means I'm going to be multiplying loads of terms with x together, and in fact on both sides I'm going to end up with a quadratic, aren't I? Because I'm going to multiply some term in x by another term in x. So I'm going to get some x squareds, and then I'll simplify them all and set them to 0 as you do, and I'll solve that quadratic. So I'll find what x is. And that means that I will have this side, because I'll be able to work out what x plus 5 is, because I'll know what x is, and I'll have this side. And then I've got to think, how do I work out what this angle is? Well, I can see that I've got the side opposite the angle here, and I've got the side opposite the angle here, and that says to me that I can use the sine rule. So this question brings together knowledge of circle theorems. You need to know intersecting chords theorem. It's not on the formula sheet. Algebraic manipulation and solving of a quadratic, and then the sine rule. And that's going to be our strategy for solving it. Okay, so I've got to do this carefully. AE is x plus 5. EC is 5x minus 12, and that's equal to BE, which is x, times ED or DE, which is x plus 12. And I've got to carefully multiply that out and get it all on one side. Let's do it. So I'm going to get 5x squared minus 12x plus 25x minus 60 on that side, which is going to be equal to x squared plus 12x on the other side. And I'm going to take away this stuff from this side, from the left-hand side, so that I have 0 on one side, and I'm going to simplify as I go. So 5x squared minus x squared is 4x squared, so that's quite nice and easy. And then I've got minus 12x plus 25x, and I want to subtract another minus 12x. So in total, I'm going to have minus 24x plus 25x, and that's just plus x on this side. And then I've got no units, so I still just keep my minus 60, and that is equal to 0. And I've now got to factor this quadratic to find solutions for x. Now that means I need to find two numbers that are 1 apart from each other, because the coefficient of x here is 1. So when I add them together, I want, sorry, they're not 1 apart from each other. When I add them together, I get 1. And when I multiply them together, I'm going to get 4 times minus 60, which gives me minus 240. I've got to think what those numbers are. So it's going to be a negative number and a positive number that, yeah, so it's going to be something like minus, 16 and plus 15 or something along those lines. I might try my calculator. I can't work that out in my head. Not now. So 15 times 16, that is 240. So I need either minus 15 plus 16, times 16, or 15 times minus 16. And I've got to use the one that's going to give me, when I add them together, plus 1. So that means minus 15 and plus 16. So I can split this middle term. Oops. 4x squared, what did I say? Minus 15x plus 16x, that still gives me just x, minus 60 equals 0. and then as usual I'll factor each half. I'm going to factor this half, and then I'm going to factor this half, and I'll show you how that works. Okay, so I can't take a unit out because 4 and 15 don't share any common factors, but I can take an x out. So that gives me an x outside and 4x minus 15 in there, plus, and I can, what's the highest I can take? I can take a 4 out, and I can't take an 8 out. So I think 4 is the highest I can take out here, and that is going to give me inside 4x minus 15. And just as a check, these two things should be the same. If they aren't, I've done something wrong and I need to go back. They are the same, so I'm happy with that. This still equals 0. And then finally I'll bring these two x and 4 together, because if I've got x lots of 4x minus 15 plus 4 lots of 4x minus 15, I must have x plus 4 lots of 4x minus 15, and that's equal to 0. So, as usual, any two things multiplied together equals 0 means that one of those two things has got to be 0. There's two ways that can happen. We could have x equals minus 4, because then we'd have minus 4 plus 4 on this side, which would equal 0. 0 times whatever is going to be equal to 0. Or, and I'll just do this quickly in my head, if I add 15 and divide by 4, it could be that x equals 15 over 4. So I've got two possible values for x. And looking at the question, it doesn't make sense for x to have a negative value, I don't think, because this can't be a negative distance. I mean, we're talking about centimetres here. This is a real world situation with a circle. So I can, at this point, reject this one here. And I'll just write reject here. Okay. Now I'm going to go up here and carry on, assuming now that x is 15 over 4. So x 15 over 4 centimeters. By the way, I'm not going to simplify that. I'm not going to change that to 3.75. I'm quite happy with it being 15 over 4, even though in the end I'm going to make a decimal solution and quote it to one decimal place. So, sine rule. This over this is equal to this over this. And that I'm going to write out. So, the sine of this, I should say. It's always the sine of the angles. So the sine of, let's say, ADE over 15 over 4 plus 5, which is 8.75, we know, but in fact maybe I'll write 8.75. It looks a bit weird to have a fraction under a fraction there. 8.75. I've got 8.75 because it's this value here opposite the angle ADE. We know that x is 3.75 and that side is 3.75 plus 5. So I've got that, and that must be equal to the sine of this angle over this value. So that's equal to the sine of 48 over 3.75 plus 12, which is 15.75. And I want to rearrange that, so I've only got the sine of ADE on one side. Or I may even get ADE on one side. I'll show you how that works anyway. The sine of ADE is going to be equal to 8.75 times the sine of 48 all over 15.75. That is sufficient working. You can now go to your calculator, even though you haven't got this. You could go an extra step here, but this is not necessary. Exam mark schemes don't insist that you do this, but you could say ADE is the inverse sine of, and you write this giant thing here, sine 48 over 15.75. But it isn't actually necessary. Either of those is sufficient. You have to write one or the other, but having done that, you can go straight to your calculator. Well, I will do that now. Let's move this if I can. So I want the inverse sine, I want the inverse sine of something. That something is a fraction. On the top I've got 8.75 times the sine of 48, close bracket, and on the bottom I've got 15.75, and that's given me equals 20. Let's get it back so I can see what it was. 24.384, etc. 24.384, blah blah blah. But the question's asked for corrected decimal, one decimal place, equals 24.421 decimal place. And that's your answer. Quite a nice question because it brings together lots of different stuff. There is, of course, the ambiguous case with the sine rule, but that can only happen if you think that this angle might be obtuse. And it manifestly it isn't. I think you can assume in this question that it isn't. It would have to be unbelievably inaccurately drawn. So we just assume that it isn't obtuse. If it were obtuse, you would have to take the result 24. The result 24.4 away from 180. But that would make it an extremely sort of large angle, and in fact, I don't even think it would be possible. So I've ignored the ambiguous case here.